Today I would like to discuss auxiliary heating and current drive in Tokamak. Probably this will be our last talk on Tokamak. Today we will begin rather with the overview of Tokamak operation that we discussed in some length last time. We will go over to radio frequency current drive in Tokamak, radio frequency heating in Tokamak, then neutral beam heating in a Tokamak, and finally I would like to give you a perspective on international thermonuclear experimental reactor called ITER, which is being built in France. Well, these will be the references for today's presentation. Let me begin with an overview of Tokamak operation. Tokamak, the cross section of a Tokamak I can simply build like this, make like this, and this would have a plasma in the center. So, this is a plasma here, and obviously this is something system is going like this. And this is blanket. So, in the plasma, which is deuterium-tritium mix, when the thermonuclear fusion reactions produce neutrons and alpha particles, we would be aiming at absorbing the alpha particles within the plasma to sustain the burn, whereas the neutrons cannot be absorbed and they will be moving out of the plasma. So, this will be primarily a lithium blanket, and that will absorb the neutrons and get heated. So, this becomes like a heat reservoir, and some coolant will transfer heat from here into what we call as the heat exchanger. So, in this there will be a coolant which will be bringing in here and taking heat from here into here. So, this is a coolant, and this is we call heat exchanger. Well, this has to be coupled to a turbine, because this heat energy has to be converted to mechanical energy. So, we would like to connect this to a turbine, and that will be, so this is a turbine, and this will be connected to a generator. So, this is generator that will convert the mechanical energy into electrical energy. So, this is electrical power. Our physics has been primarily focused on the plasma, how to confine the plasma, how to heat it to a required temperature of 10 keV, and how to drive a current that is essential for confinement of the plasma. So, always keep this in view that we have to sustain a burn by alpha particles. We have to confine the plasma by a mix of a toroidal magnetic field and a poloidal magnetic field. So, the system is going to require a current typically of the order of several mega amperes. Now, how can we do this? By using waves or particles launched from outside. If you want to do this, well, this is really done in two ways. One by radio frequency waves. They can drive a current in the plasma, and they can also provide additional heating, because a study we learnt that ohmic heating can heat the particles up to a temperature of about 1 or 2 keV, but the goal is 10 keV. So, additional heating is required. This can be provided by radio frequency waves or by neutral beams. Neutral particle beams are required because charged particles cannot penetrate the tokamak, as they will have to cross the lines of force to reach the center of a tokamak, a plasma, and charged particles will experience a Lorentz force and they will not penetrate. Hence, neutral beams have to be launched into the system, if at all particles have to be launched from outside. So, today we will discuss the efficacy or effectiveness of these two systems. Radio frequency waves, well, are primarily electromagnetic waves that are launched from outside, and once they reach into the plasma, they can mode convert themselves into electrostatic waves. Some of the waves can mode convert themselves into electrostatic waves, for which magnetic field is very weak, but the electric field is primarily in the direction of k vector of the wave. But those waves can effectively heat the particles. We shall learn some aspect of that process. But before that, let us have some estimate what kind of powers are required. In a tokamak, we are going to have particles with electron and ion density is equal to 2n. N is the density of electrons and n is also the density of ions, deuterium, tritium ions. So, 2n is the total number of particles, and each particle is going to have 3 by 2 into T, where T is the temperature of the particles, as the kinetic energy of each space of each particle. So, this is the total energy density in the plasma. If I multiply this by the volume of the plasma, then this quantity is the total thermal energy contained in electrons and ions in the plasma, and if this is lost in a time of the order of energy confinement time tau e, then this is the power lost in the system from the system per second. So, this is to be replenished, this should be provided by the RF or by the neutral beams once the ohmic heating is removed. This is the power that the RF has to provide. If I put typical parameters like R of the order of 1.5 meter major radius, minor radius of tokamak around R by 3, like aspect ratio is 1/3, then this quantity turns out to be typically, if I put the numbers, and T temperature is equal to 10 keV, density around 10 to the power 14 per centimeter cube, then this number turns out to be around 4 into 10 to 6 upon tau e. If this is in seconds, then this is in watt. So, you require, if I take tau e around 1 second, then you require this about 4 megawatt. For ITER kind of tokamak, where the volume is much larger, one should envisage powers typically of the order of 100 megawatt. So, we are targeting particles, particle beams or neutral beams or radio frequency waves with powers of the order of 100 megawatt. So, powers that we are requiring is 100 megawatt. Now, if we are using neutral beams, then the power, so power required is typically in the domain of 10 to 100 megawatt. Radio frequency sources of such high power exist in the microwave range, they also exist in the millimeter wave range, and they also exist at lower frequencies. So, this part is we are comfortable at least as with the availability of powers. Now, let me typically mention that these plasmas have magnetic field B, phi and BP. BP is smaller, polarized magnetic field is smaller, and B phi is in the range like 4 to 10 Tesla. Total magnetic field in the system is around this, and this corresponds to a electron cyclotron frequency omega c upon 2 pi, so that it becomes in Hertz around 30 T in gigahertz. If I choose at 1 Tesla, let me put this B phi, 30 B phi. So, if I choose the magnetic field in the tokamak as 1 Tesla, this will be 30 gigahertz. If I choose like 4 Tesla, then this will be 120 gigahertz. 120 gigahertz is a millimeter wave of about 1/4 centimeter wavelength. Conventional klystrons, magnetrons do not operate at those high frequencies. Even travelling wave tube does not operate. So, one has to go for gyrotron. And if we want to go to 10 Tesla tokamak with 10 Tesla magnetic field, then this will be 300. So, this is equal to 300 gigahertz at B phi is equal to 10 Tesla, which is a very high frequency like 0.3 terahertz, and a device that can produce power, radio frequency power at this high frequency is primarily free electron laser. But if you are operating a tokamak at 4 Tesla magnetic field, and if you want to use electron cyclotron resonance or waves of frequency close to electron cyclotron frequency, then one should aim at frequencies around 120 gigahertz. Some gyrotrons can operate at those frequencies, and the efficiency of gyrotron is also quite high. So, I think we have reasonably efficient sources of power at electron cyclotron resonant frequency. However, if you are interested in heating the ions via ion cyclotron resonance, then the ion cyclotron frequency, there are two kinds of ions in tokamak, deuterium and tritium. Suppose I want for deuterium, then this quantity would be mass ratio times is smaller. So, this will be mass ratio is typically 4000 as compared to electron mass. So, this becomes 30 upon 4000 B phi. So, if I am having a tokamak with 10 Tesla magnetic field, this will be 300 upon, and this is in gigahertz. So, this will be typically of the order of at 10 Tesla, maybe let me call it 4 Tesla. At 4 Tesla, this will be 4 will cancel out with this 4, and this will be 30 divided by 1000. So, 3 by 100, 3 by 100 gigahertz. So, this will be 30 megahertz, I guess, at 4 Tesla magnetic field. I think, so if I put B phi is equal to 4, 4 will cancel out, 1 0 will cancel out. So, this becomes 3 upon 100 gigahertz or 30 megahertz, which is right. So, then you should be aiming, so for ion cyclotron resonance, if you want to choose the radiation frequency close to ion cyclotron frequency, then you require a radio frequency wave of frequency about 30 megahertz. One can also choose Elfin waves whose frequencies are smaller than this frequency. Now, as far as neutral beams are concerned, neutral beams typically have beam energy EB of the order of 100 kilo electron volt. Normally people produce deuterium beams or hydrogen beams, neutralized deuterium typically, and the beam energies are around 100 keV or less, 80-90 keV, something like that. That is the kind of beam energy. And if you want to produce beam power of the order of 100 megawatt, then the beam current you can estimate. This will be about a kilo ampere typically, because it is the product of these two that gives the power. So, we are really talking about neutral beams of very large currents. Now, before I go into the neutral beam heating, let me talk something about the current drive by using RF in the plasma. RF current drive. Yesterday, I mentioned to you that in a tokamak, if you want to draw a toroidal current, then it will be preferred if the current is carried by energetic particles. The particles which gyrate, which rotate with the velocity v phi in the toroidal direction, this is called toroidal direction. Then a particle of charge E magnitude wise and moving with velocity v phi, well, not v phi rather, covering one circle in time t will produce so much current in the system. A charged particle of charge E, if it is rotating, making one circle complete in time t, so this I called as rotation time Tr, rotation period, then, and this can be written as typically E upon 2 pi r upon v phi, because the time it takes to go round once is equal to the distance it has to cover divided by the velocity along the line of force. So, typically this is the quantity. So, current is proportional to velocity, and these electrons suffer collisions, and I mentioned the collisional drag was m v phi is the momentum which is lost in one collision, and if there are new collisions per second, so much is the momentum lost by these particles via collisions. And this is the kind of momentum should be supplied to the electron per second, means so much force must act on the particle, and the distance traveled by particle per second is v phi. So, this is the kind of energy lost by the agency that is providing momentum to particle. So, this is the work done, this is the current drive by single particle, and this is the energy given to single particle per second. So, if I drive the two, divided the two, then the efficiency of current drive, which is the current divided by the energy lost, this is equal to, divide the two, and you get this is equal to E upon 2 pi r, r is the major radius of the tokamak, into m nu into v phi. Since nu goes as v phi to the power minus 3, hence this efficiency of current drive goes as v phi square. Hence, it is always preferable to have current driven by the fast electrons. And typical values that you can achieve by this, if the current is driven by 100 kV electrons, then this efficiency can be of the order of 1 ampere per watt. which is very reasonable thing that has been achieved also. So, if you want to drive a 100, say 10 megampere current, then you require 10 megawatt RF power. This is what I want to convey here. If the energy is deposited on fast electrons. So, that is something to be kept in view. And if you look at the distribution function of electrons in a tokamak, let me plot here F versus V phi. V phi normally we call in plasmas V parallel, because this is parallel to the phi direction or azimuthal magnetic field direction. The distribution function, if it were Maxwellian, it will be like this. However, in tokamak, the distribution function has a longer tail. And these are the high velocity particles that carry effectively the current. And what you want is that the radio frequency wave that you want to launch from outside should deposit its momentum and energy on particles which are here, means it should resonantly interact with particles with large V parallel. Now, when we were discussing the true stream instability, we mentioned that if there is a wave, plasma wave, and plasma wave we consider of this form, phi is equal to some amplitude A, e to the power minus I, omega t minus k z z, and we consider the propagation of an electron beam with velocity v0 b also in the z direction, then we found that the wave can be driven unstable if omega is close to omega p, which is the natural frequency of plasma oscillation or plasma wave, and also when omega is simultaneously equal to kz v0 b, or slightly bigger than this, not slightly bigger, rather slightly less than this, minus we call it some delta r, slightly less than this. The reason was that when the phase velocity of the wave omega by kz is equal to v0 b minus a small quantity, then the electron deposits energy on the wave. In the other case, when omega by kz, which is the phase velocity of the wave, is more than v0 b, in that case reverse happens, means energy goes from the wave to the particle. Sorry. Yeah. So, instability occurs when the wave amplitude grows and beam has to move faster than the wave. So, what you really require that for resonant interaction this condition should be satisfied and wave frequency should be close to some normal eigen frequency in the system, normal frequency of any electrostatic wave in the system. In a unmagnetized plasma, there are only three kinds of waves: Langmuir wave, ionoacoustic wave, and electromagnetic wave. Electromagnetic wave is a transverse wave which cannot be driven unstable by an electron beam. So, it is only there are only two electrostatic waves. One is a high frequency electrostatic wave called plasma wave or Langmuir wave, and the ionoacoustic wave is a low frequency wave whose frequency is less than the ion plasma frequency. So, you have very limited choice. However, in a tokamak there is a magnetic field, and magnetic field allows a much larger variety of electrostatic waves in the plasma, and there is some beauty in that. Let me mention something. First of all, the Langmuir wave breaks into two branches. One is called lower hybrid wave, and upper hybrid wave. lower hybrid wave has an interesting property. If I choose a plasma of plasma frequency greater than cyclotron frequency and plot the frequency of this mode lower hybrid wave as a function of say k, well, if I consider a plasma in which there is a magnetic field in the z direction, a static magnetic field. So, suppose this is the direction of a static magnetic field and my wave is going at some angle. So, this is the k vector of the wave. It is an electrostatic wave whose electric field I express as minus gradient of some potential phi, and suppose this moves some angle. So, this I choose as my z axis, the direction of static magnetic field, and wave travels at some angle. So, if we plot kz by k of this wave, this is suppose omega p somewhere, this is suppose omega c somewhere. This wave when kz is 0 has a very low frequency and the frequency becomes large when kz becomes 0. Sorry, opposite, I am sorry, I made a mistake. Omega c is large here. I think let me remove this. This portion is not. At kz equal to 0, these waves have a frequency, well, kz equal to 0 means k is parallel to perpendicular direction, and this is all right, this is all right. And this goes from here to this, when this is unity here. So, there is a frequency here which is called lower hybrid frequency omega LH, and the upper hybrid wave, if I plot this Pearson relation here, and we shall do it someday, then it varies between two frequency ranges. It starts from somewhere called upper hybrid frequency and goes like this. So, this is the frequency called upper hybrid frequency omega UH. Now, these quantities omega LH and omega UH are simply symbols. Omega LH is symbolically written for this quantity called ion plasma frequency divided by 1 plus omega p square by omega c square to the power half, where omega pi is called the ion plasma frequency, omega p is the electron plasma frequency, and omega c is the electron cyclotron frequency. So, in a plasma where omega p is much bigger than omega c, I can ignore this 1, and this quantity then becomes equal to omega ci and omega c under root, where omega ci is the ion cyclotron frequency and omega c is the electron cyclotron frequency. So, this is the hybrid between the two frequencies, whereas upper hybrid frequency omega UH is equal to omega p square plus omega c square under root. So, this is higher than omega p and omega c both. So, the plasma wave which has a frequency in a cold plasma equal to omega p splits into two different waves with very different frequencies. Actually, this is a new mode that appears. Well, the dispersion relation probably we can drive this later. We have to discuss these waves in detail in some separate lectures, but for today's purpose I would like to emphasize that a plasma supports a much larger number of waves. These two waves I simply mentioned because they are related to or similar to electron plasma wave or Langmuir wave, but then at lower frequencies you get a new variety of waves called ion cyclotron waves, ion Bernstein waves, we also get electron Bernstein waves and so on. So, a plasma has a magnetized plasma is very rich in wave phenomena, and any of these waves can be employed for plasma heating. Now, let me mention what are the basic requisites for resonant wave particle interaction. We already got a clue that a beam moving with such a velocity that the frequency of the wave as seen by the particle is nearly 0, then we say that the particle is in phase synchronism with the wave and it can very effectively exchange energy with the wave. So, the main requirement has been that find a frequency that some moving particles in the system, either electrons or ions, they see the wave to be some sort of electrostatic wave or effective frequency is 0. Now, let me consider a wave in the plasma, electrostatic wave in the plasma with amplitude A exponential minus I omega t minus kxx minus kzz. Suppose I create a wave in the plasma via mode conversion from an electromagnetic wave launched from outside, and the plasma it has become this kind of wave. Now, if the system has electrons which are gyrating over the lines of force, because there is magnetic field is here, so the electrons are gyrating over the lines of force, they are going like this. And we had solved for the equation of motion for electrons in a straight line geometry. When the lines of force are straight, we found that if the system has magnetic field along z axis, then the particle trajectories were something like this. Particle velocity was, zeroth order velocity was v0x is equal to v0 perp cos omega ct, where omega c is the electron cyclotron frequency. v0y was v0 perp sin omega ct. X was guiding center coordinate plus v0 perp upon omega c sin omega ct. Y was yg minus v0 perp upon omega c cos omega ct, and z was equal to some constant plus v0 into t. So, this is a representation of particle trajectories, particle coordinates when there was no wave. Now, these particles, when they see a wave, obviously if the, and suppose the wave amplitude is very low, then we say that x will be modified, y will be modified, z will be modified, velocities will be modified just a little. But primarily the x coordinate of the particle, because it is changing with time originally, and consequently the field or potential of the wave as seen by this electron will have x as a function of time. Put this x in here, put this y in here, there is no y here, so do not have to use this, but put this z here, then you will find that there is a time dependence not only coming through frequency, through this omega t term, it comes through here as well as here. So, effective frequency of the wave is no longer omega, it is modified because of dependence of x and z on time. Let me use these two in here. The problem would come that when I substitute this here, let us see what do I get. My phi becomes the potential of the wave as seen by a moving particle, which is gyrating particle rather, becomes a exponential minus I, omega t remains as such. Now, this kx x terms becomes minus kx into xg, then there is a term here minus kx v0 perp upon omega c into sin omega c t, then this is kz, then z0 minus kz v0z into t. These are all in exponents, exponential. What you can do, combine this t term with this t term, but this is a term which is a little complicated. because in the exponential you are getting sine omega ct, but there is identity called Bessel function identity, that whenever you have a term like this I alpha sine theta, this you can always write as a sum over integer n, which goes from minus infinity to plus infinity, Bessel function of order n and argument alpha, exponential of I n theta. So, what you get here, this term is getting exponential of I kx v0 perp upon omega c into sin omega ct. This should be how much? This is like alpha and this is like theta. This becomes summation over n j n of kx v0 perp upon omega c exponential of I n omega c t. Means this term is equivalent to many terms having their frequencies time dependence at multiples of cyclotron frequency, 1 omega c, 2 omega c, 3 omega c, etc., and n can take negative integer values also. So, when I substitute this expansion in here, then expression for phi becomes your phi turns out to be equal to a, or rather summation over n many terms a j n of argument kx v0 perp upon omega c, and the frequencies turn out to be exponential minus I omega minus n omega c minus kz v0 z into t and minus kx xg minus kz z0. This is the kind of expression we get for phi. My main point was that a wave of frequency omega, when viewed by a gyrating and moving electron, the frequency is no longer omega, but it is omega dash or omega n, rather I will call it omega n, which becomes omega minus n omega c minus kz v0 z. And if you can choose your particle velocity v0 z and n in such a way that this becomes a 0, then we say that for the particle the wave field will appear like a DC field. And so phase synchronism will occur occurs means the particle will the electron will always see the field as a DC field when omega n is 0. So, omega minus n omega c minus kz v0 z is equal to 0. Obviously, for all n this cannot be satisfied simultaneously. For some particles moving with some velocity v0 z, this will be satisfied for some specific value of n. When this is satisfied for n equal to 0 case, then we call this resonance a Cherenkov resonance. This is called Cherenkov resonance. And when this is satisfied for n equal to 1, then we call this cyclotron resonance. Omega minus n omega c minus kz v0 z is equal to 0, we call it cyclotron resonance. Important thing of the magnetic field, please note, when there was no magnetic field, this was missing. So, magnetic field opens up a new possibility of several resonances corresponding to different values of n. However, these resonances are significant only when the argument of the Bessel function is significant. So, V0 perf is what? In a thermalized plasma, Maxwellian plasma, electrons are gyrating, different electrons are gyrating with different velocities. So, some typical average velocity I can take to be like thermal velocity. So, whenever kx V thermal upon omega c is comparable to 1, not too small. If it is too small, then only n equal to 0 term survives, other terms are not important. So, what you require is that this should be significantly comparable to unity or bigger. When this is comparable to n, then this is very substantial. So, if I want this equation to be satisfied for nth harmonic, cyclotron harmonic, then I must choose those waves for which kx V0 V thermal upon omega c is comparable to n, if possible. You can achieve this condition for ion cyclotron ions also, and consequently those waves for which this condition is satisfied for ions, they can directly heat the ions, and which is what ion cyclotron waves or ion-ion hybrid waves do. So, this is an important thing that we should keep in our head, that if you want to drive current, then you are expecting to, or rather you want the energy to be deposited into only electrons, and hence this kind of condition should be satisfied on electrons, because this condition will be satisfied with electrons of lower velocity. This will be satisfied on electrons of larger velocity. So, this is a more preferred condition. However, people have employed this condition as well. So, depending on at what value of kz the wave is launched, the interesting thing is that you can preferentially deposit your energy only on those electrons for which this condition is satisfied. If there is a spread in velocity distribution of electrons, then only those electrons will be satisfying this condition for which the velocity V0z is omega by kz. And if I choose my lower hybrid wave, for instance, with omega by kz around half c by 2, half the light velocity, then V0z will be like c by 2. Those electrons with V0z equal to c by 2 will be absorbing the lower hybrid wave preferentially, and hence they are the ones that are needed for current drive. So, for lower hybrid current drive, what we require is Vz of the order of c by 2, which is something electrons like 100 keV electrons. For this you will require omega by kz equal to c by 2, and this corresponds to eta z or eta parallel that we call as, which is defined as c kz upon omega. This should be around 2. There is a serious matter. In free space, if you launch a wave, then kz certainly is less than omega by c. Any component of k cannot be more than that. But if you have this kind of situation, then other component of kx will, like kx, will be imaginary, because k square in free space is equal to omega square by c square. So, this is kx square plus kz square. If I write, then this requires kx square is equal to omega square by c square minus kz square, and that will be less than 0 because kz is too big. So, how will you create this kind of wave? This is normally done by using a phased antenna array. So, if you have a tokamak like this, in which you want to drive a current, then you have a waveguide array here, which is essentially not a single waveguide, array of many waveguides, this. These waveguides are traveling like this. and in the successive waveguides you are launching waves. In every waveguide wave is coming, but they are not in the same phase. So, this wave coming in this waveguide will have one phase, the wave coming in the second waveguide will have a different phase, the one in the third one have a different phase, and so on. So, by properly phasing these waveguides, you can make your wave that is launched here to travel in a particular direction like this. The wave is evanescent from the exit to the waveguide to the plasma, but right when it enters into the plasma it becomes a propagating mode, and this can hit the plasma. I think details of this scheme we will discuss once we have discussed the electrostatic waves in plasmas, magnetized plasmas, and that we should do later. So, I will defer this discussion to a later stage, but let me now mention about neutral beam heating. For neutral beam heating, usually one employs deuterium beams, and the system is something like this. You have a ion source here, this is ion source or deuterium source, and there is some accelerator here, a negative grid with large potential difference, so that the ions are pulled with large velocity, and then this is a charge exchanger or neutralizer, in which deuterium ions enter here. From this ion source deuterium ions are pulled, this is the accelerator, and these deuterium ions are then neutralized. So, from here you get two kinds of particles, one of them are neutral deuterium atoms, and then some deuterium ions are also residual ions are there. So, you pass this mixture through a magnetic field, which I will designate like this, which is called deflector magnet, deflector magnet, and that will make the D0 uncharged deuterium atoms to travel like this. So, D0 go like this, and then they hit the plasma here. So, plasma is somewhere here, Tokamak plasma is somewhere there, whereas the ionized deuterium or deuterium ions will be deflected out. This is called neutralizer or charge exchanger. And the ion source has a very typical structure. It is called a multipolar cusp. Let me tell you what is a cusp. If you have a coil, magnetic field coil like this, which carries current in one direction, and you have another field coil that has current in the opposite direction, then the lines of force here will be like this, they will be diverging, and from here they will be in the opposite direction. So, the lines of force are like these. This is called a magnetic cusp. So, magnetic field is quite small in this region, large all around. So, this is called a simple magnetic cusp. And what kind of ion source you have? You have a large number of permanent magnets with north and south pole opposite to each other. So, you have this structure here, you have many these bar magnets with opposite polarities, like if this is north here, then this is also north here, this is north here, this is also north here, this is south here, then this is also south here, and so on. So, place them in such a fashion, many such magnets, then the magnetic field that they produce in this region is called multipolar cusp B field, and hot wire cathodes are mounted in between these regions. So, they produce hot wire cathode something like these. You have to mount them in between these two. This a hot wire cathode comes in here, So, you pass a current through this wire and then the electrons are emitted and the gas gets ionized. So, a plasma is formed here, and from the plasma, this is deuterium plasma you form here, and deuterium ions are pulled, and then you get this beam. So, this is a schematic of this. Now, the physics is rather simple. First of all, the neutralizer, what does it do? In a neutralizer, the deuterium ions collide with deuterium gas molecules and they undergo exchange collisions. So, this produces deuterium without any charge plus D2 ion is created like that. So, this is a slow ion because the molecule was slow, only the electron has been transferred from deuterium molecule to deuterium ion. So, this is an energetic particle, this is the required neutral beam. This forms actually neutral beam. And the typical charge exchange cross section is around 3 into 10 to the power minus 14 centimeter square, and roughly, well, this is actually sensitive to energy. This is probably the maximum value. I am saying that if you are having energy in the energy range, deuterium ions in the energy range 20 to 100 keV, then you get 85% ions getting neutralized when they emerge. Otherwise, when the energy is increased, then this reduces to about 40%. So, charge exchange, this is the efficiency of charge exchange, 85% ions will get neutralized if the energy is around this, but the typical energies required for Tokamak neutral beam heating are around 100 keV. So, I would say that roughly half the ions get neutralized. So, you get a neutral beam. Now, these ions, when they enter into the Tokamak plasma, you have a Tokamak somewhere here. This is the cross section of a Tokamak. Sorry, the Tokamak is like this. This is a torus, this is a cross section of a Tokamak. You can launch neutral beam either tangentially. Actually, let me just draw another picture here. This is important. Cross section by, if you see from the bottom, the Tokamak will look like this. So, what you can do, if you launch your neutral beam here, it will have a long distance to travel. So, you can launch this neutral beam through here, or you can launch your neutral beam through here. If you are launching neutral beam like this, then it has only very small distance to travel. Obviously, this is also quite large, but this has a much larger distance. So, it is preferable to launch your neutral beam through here, and in this, the neutral beam as it travels, it will lose its energy, and if neutral beam current I define IB, then as it travels in this direction, let me call the direction as x, some direction x, then this is equal to minus the density of neutral beams into charge exchange collision cross section into beam current. IB, I am defining a quantity which is the product of beam density multiplied by beam velocity. This n is the density of ions. So, the neutral beam as it travels will lose its energy, and typically in a distance of about 30 centimeters it loses complete energy. So, the neutral beam that we launch can cross plasma, can cross the magnetic field and reach the main body of the plasma, and then it gets totally ionized, and then it can deposit primarily its energy on the ions. So, this is a very important scheme of plasma heating, and I think all supplementary heating schemes will employ neutral beam, whether it is ITER certainly is envisaging using neutral beam heating, And other devices also, all experimental tokamaks are, large size tokamaks are employing neutral beams for heating. And I think I will stop at this stage. Thank you.